Let's understand the difference between solids and fluids in terms of their reaction against the applied shear stress. Let's first understand what happens to the solid when the external shear stress is applied on it. So let's consider a solid. In the coordinate axis x, y and z, and let's say the coordinate axis is such that this is x, this is y and this is z. Now let the dimensions of the solid be like: the length in the x direction is L, the height of this solid along the y direction is h, and the length along the z axis or the depth is W. And let's say W, the length along the z axis, is very greater than the length along the y axis or the height of this block h. Let's say now a force Fx is applied on the top surface of this solid. So this is the top surface, and a force Fx, since it is in x direction, I have written this subscript x. On the top surface, a force Fx is applied tangential to the surface, and this bottom part or the bottom surface of the solid is kept stationary. Now given this case that W is very greater than h for the solid, we can safely assume that the variations in the z direction are negligible as compared to the variations in the x and y directions. So let me just quickly write it down. So for this condition, the variations in z direction are negligible as compared to the variations in x and y direction. So now, since this third dimension is not important, we can visualize this problem in just 2D. So in 2D, this problem would look like that we have this surface, the height is h, the length is L, and a force Fx is applied on top of the surface. The bottom surface is kept stationary, so this is stationary. Now let's understand what will happen to this solid when this Fx is continuously applied on this surface with the lower surface kept stationary. So let's say at t equal to 0, when the force is not applied, this is my surface, and I am marking points on the surface to understand how those points on the surface would change when the force Fx is applied. So let's mark these points on the surface. Let's say there are these 3 points on the surface that I have marked before the application of Fx. So this is at t is equal to 0 and Fx is not applied. Or better, let's exaggerate this figure to understand better. So let's exaggerate this figure. So this, if I make this larger, this would look like that. This is your h, the bottom plate is held stationary, and let's say I'm marking some points on the solid. So these points mean that these points are when the solid is in undeformed state. Solid is in undeformed state. Okay. Now let's say the force Fx is applied on this solid. A force Fx is applied on the top plate of this solid, and the solid deforms. So now let's say the deformed state of the solid looks something like this. So it would look like this, it would look like that. So it would get deformed, and let's say now the location of these points changes. So let's just mark it with a green color. So the location of these points change when Fx is applied. Okay, so this should look like, actually, sorry, so this should look like this. Okay, so this, just let me write it. So this green refers to solid in deformed state. Now in case of the solids, it has been seen that with respect to, let's say, with time, you continuously apply this force Fx, so this is continuously applied with time, then initially there is some deformation in the solid, and because of the internal stresses inside the solid resists the further deformation. So these points would not move with time, so they will remain at this angle, and let's say this angle is alpha. Okay, and it has also been seen that this value of this alpha depends linearly on this Fx. So if you go on increasing the magnitude of the force, this angle of deformation will also increase linearly. So again, so let me repeat it. So we have a solid, the bottom surface of the solid is held stationary, the top surface of the solid has been applied a force Fx tangential to the surface. This is my coordinate axis, and given these dimensions of the solid, W very greater than h, we can safely assume the variation in z directions are negligible, and we can just study in the solid being deformed in 2D. The 2D is, it is in x and y, and we are not now looking the variations in the z axis, and we just exaggerated this figure like this. We marked some points, so these are the black points that corresponded to the undeformed state of the solid. The green points were marked that refers to the deformed state of the solid. A force Fx is continuously applied, and this Fx is, the magnitude is constant, its magnitude is constant with respect to time. So this would, the force profile would look like this with respect to time. The force Fx is, the magnitude is constant in time. Okay, and this, and if you want to understand how this alpha varies with respect to the magnitude, so let's say if I am applying let's say 2 newtons, there would be, let's say, some alpha 1. If I am applying 4 newtons, this angle, this would be 2 alpha 1, because I have doubled the force, I will get double the value of this angle. Okay, and also keep in mind that this force Fx is small enough, is not very large, so this is enough to cause the deformation of the solid, but not enough to break the solid. Okay, for such kind of deformations, this alpha is, which is the angular deformation in the solid, this is commonly referred to as shear strain. Now when a solid is deformed to an angle alpha, there are internal stresses which generate inside the solid. So these stresses, to quantify this, so we define shear stress inside the solid, shear stress tau inside the solid, that has been seen to be proportional to this alpha. So this shear stress tau has been observed to be proportional to this alpha. Okay, now if the deformations are small, we can write alpha nearly equal to tan of alpha. So we can replace this alpha with tan alpha for small deformations, right? Now from the figure, so let's say this is delta L and I've written that this is H. What would be tan alpha? So tan alpha would be this by this, delta L by H. Now the proportionality constant is the elastic modulus of the solid, delta G into delta L by H, and this G is called the elastic modulus of the solid, or also called the modulus of elasticity, modulus of elasticity. From your high school, you can recognize this equation, stress developed inside the solid proportional to strain. This is what it is called. It is called Hooke's law, right? So from this simple analysis, we could reach to an important law, the Hooke's law, followed by the solid. Similarly, we want to understand from similar analysis some law which is followed by the fluids. Okay, so let's now do the similar analysis for the fluids. So now we want to analyze what happens to fluid. So I have just copy pasted some figures from the previous part. So this is, again, let's assume a hypothetical experiment that we have a fluid element and a force Fx is applied on the top part of this fluid element surface. Again, we are defining W very greater than H. Again, we can visualize this problem in 2 dimensions, x and y, and we are saying that if W is greater than H, the variations in the z direction is negligible as compared to the variations in the x and y directions. We can visualize this problem, thus we can visualize this problem in x and y. So again, we can visualize that this is what I would see the surface in the xy direction. From the in the xy coordinates, a force Fx is applied on top of the surface of this fluid element. The height is h, this is L. Again, this part is held stationary. Now again, if I just exaggerate this figure, this would look like this. Let's say a force Fx is applied on top surface, and thus the magnitude of this force is constant, and again the time, with time this force would look like this. So again, with time this is constant, so this is Fx. Now what happens in case of the fluid? So I have just replaced the word solid with fluid here. Again, the red black dots are telling me that these are the points on the fluid element at time t equal to 0 in the undeformed state, and then at time t equal to t plus delta t, a force Fx is applied, and let's say the green points, they tell me how are these points change when a force Fx is applied for time t. So now in case of the fluids, this figure is actually incorrect. Why? Because in the solids, if you apply some force, some small force, the internal stresses are developed inside the solid to resist those deformations inside the solid. but the similar case is not true for fluids. So what would happen now in case of the fluids is that this angle alpha will keep on changing with time as a constant force Fx is applied with time. So how would it look like? Let's understand. So this green would not actually tell me the fluid in deformed state at all times. Instead, it would tell me that the fluid is in deformed state at, let's say, at t is equal to t1. Now with time this would go on changing, this angle would go on changing, and let's assign at t equal to t2 the points would look like this. The angle alpha would increase. So let's say this angle, okay, how should I write it? So let's say this angle is now alpha 2. So these points would refer when the fluid is in deformed state at time t is equal to t2, and let's say the angle alpha, or usually called the strain, is alpha for this case, and the angle alpha the strain for this case is alpha 2. It has been seen for the fluids that if your time t2 if t2 is equal to 2t1, this alpha 2 is also 2 alpha. Okay, so now also in case of the fluids, it is seen that if you go on increasing the magnitude of this force, now alpha by t instead of alpha, okay, so it should be in the y-axis, alpha by t, and this is f, alpha by t instead of alpha varies linearly. Okay, so this is the most important thing which is for the fluids different from solids. So the shear stress developed, so the shear stress tau developed inside the fluid, it is proportional to alpha by delta t. Okay, now again, since like in solids, for small deformations this alpha can be replaced with tan alpha, and this tan alpha can be written, so we just see here, this tan alpha will be written like delta L by H, and delta T was here, so we'll just write it. Okay, now if you see, what would be delta L by delta T? It would be nothing but the velocity of this top plate, right? So we can write this as the velocity of this top plate divided by this height h. So this v is the velocity of top plate. So if I remove this proportionality constant, I would get tau equal to eta times v by h, with this eta known as the dynamic viscosity or absolute viscosity, or simply the viscosity of the fluid. Okay, this eta is not, so this dynamic viscosity or the viscosity of the fluid is generally denoted as mu instead of eta. So let's just write it mu V by H. Okay. Now I can also write this V by H term. So this is your mu and this is your V by H. This can also be written like the velocity at y is equal to h minus velocity at y is equal to 0 divided by y is equal to h minus y is equal to y equal to 0, right? Can we write this? Okay. So now what we usually, like I said in the continuum approximation, this fluid element is infinitesimally small. Okay, so in that case this y is equal to h minus y is equal to 0 is very small. So then how would the situation look like? So this is your, let's say, infinitesimal fluid element, and the upper layer, let's say this has some velocity and this lower layer has some velocity. So this would be velocity at y is equal to y plus delta y. So let's say this is your delta y and this is velocity at y is equal to y. Okay, and there is a very small deformation, delta alpha. So the shear stress in this fluid element can then be given by, so tau is equal to mu, and this expression can become derivative, right? So let's write it again. So this expression, velocity at y is equal to h minus velocity at y is equal to 0 divided by y is equal to h minus y equal to 0 with limit h going very small. This can be written as dv or du. So let's say this is du by dy. We can write it like, right? So then this shear stress tau will be written mu du by dy. This expression is commonly known as Newton's law of viscosity, with this mu called the absolute viscosity or the dynamic viscosity. Okay, so let's again just briefly repeat this derivation. So we took a fluid and subjected to a force Fx on top of its plate, on its top surface, and we kept the lower surface stationary. Now I have done a mistake in this portion. Maybe you have figured it out in the whole derivation. So what is the mistake in this derivation? So the mistake is the following. So when a continuous force is applied on top plate, this top plate would accelerate, okay, and would not have a constant velocity, like I said here, as v, right? So this analysis is not done for a continuous force like we did for solid. In this analysis what we say is that this top plate moves with a velocity, let's say v, okay, and this force fx is not there. It is always moving. Since there is a constant force, this is not a constant force which is acting on the top surface. The top surface is moving with velocity v, so forget about fx in this case, okay. So the velocity of the fluid with respect to time, of the top surface of the fluid with respect to time, is constant. So it has nothing to do with force. I'm sorry for that. Okay, so the fx term will not come in this whole analysis. So the problem, we studied the problem of a fluid element with its top surface moving with a velocity v. What law would that fluid element would follow? And with this simple analysis we came up with the answer that it follows this Newton's law of viscosity. Okay, so Newton's law of viscosity tells me that the stresses built inside the fluid to oppose the shearing of the fluid because of some shear strain rate, they are proportional to that shear strain rate, and the proportionality constant is the viscosity of the fluid. So the viscosity of the fluid is a property of the fluid which represents the fluid's resistance towards the flow. Okay, so let's just quickly go through some typical values of the fluids that you see around in your day-to-day life. So at room temperature T, we have a fluid and its viscosity mu. By the way, what would be the units of viscosity? So we go in this formula. So this is your shear stress. The unit of shear stress is same as the unit of pressure, which is Pascal. Okay, let's just write it with some other color. So this has units of Pascal, and then you have this mu, whose units we want to find, and so this is your mu. Then you have this du by dy. So u has the dimensions of meters per second, and y has the dimensions of meters. Meter would cancel, and your the dimensions or the units of your mu would be Pascal second. Okay, so this the units of mu is in, let's say, Pascal second. So the values are the following. Air has viscosity of 10 to the power minus 5 Pascal second. Then water has viscosity 10 to the minus 3, 100 times of that of air. Then blood is slightly more viscous than your water. Okay, now during this derivation we assumed that during the shearing of the fluid, during the shearing of the fluid, when a velocity v is there for the top surface of the fluid, we assume that this mu value remains constant. Okay, now it's not always the case that this mu remains constant. As you apply more strain rate, so the category of the fluids which follow this equation of Newton's law of viscosity are called Newtonian fluids. and the ones which do not follow this equation are called as the non-Newtonian fluids. So let's say if I plot shear stress developed inside the fluid as a function of strain rate, I would expect that for a Newtonian fluid, since the expression for the Newton's, so let's again write Newton's law of viscosity. Newton's law of viscosity. What was Newton's law of viscosity? Tau is equal to mu du by dy. Okay, right? So this is your strain rate and this is your shear stress. So what would be shear stress by strain rate? This would be this absolute viscosity. Okay, so if I plot shear stress versus strain rate, I should expect for the fluids that follows this Newton's law of viscosity or the Newtonian fluid, I would expect a straight line with its slope value, representing the dynamic viscosity, representing the absolute viscosity mu. Okay, right? So there are certain category of fluids which don't follow this behavior. So let's talk about them one after the other. One category of fluids show this kind of behavior. These kind of materials are called Bingham Plastics. The example of Bingham Plastics are ketchup, the tomato ketchup that you like with potatoes, and the other example is the one that you use daily in the morning or maybe in the night, that is toothpaste. So what happens for such Bingham Plastics? So let's assume this is your Bingham plastic. Okay, so let's say that you have, let's say this is V and the deformation is very small. Okay, this alpha is very, very small. Now if this deformation is very small and due to this, let's say the shear stress developed inside the fluid is very less, then these kind of fluids behave like solids if the stress developed is lesser than, let's say, this value. Okay, now if you go on increasing this V, that is go on increasing this deformation such that the stress value is reached till this critical value, then suddenly these fluids will act like the normal fluids. So in your toothpaste, initially the toothpaste behaves like a solid. Now as you increase the deformation or the deformation rate such that this critical value is achieved, the toothpaste would behave like a simple Newtonian fluid. You must have observed this also, right? There are some other category of fluids that follow this kind of behavior, Such kind of fluids are called shear thickening fluids. The example for such fluids is cornstarch. So what is happening for these fluids is that when you go on increasing the strain rate, the slope value goes on increasing, and slope is the viscosity. So as you go on increasing the strain rate, the viscosity of that fluid goes on increasing. The other category of fluids follow this behavior. So you can see that the viscosity decreases as you go on increasing the strain rate. These are called shear thickening fluids. Shear thinning fluids. The example is the paints that you use in your home. To observe how these viscosities change with strain rate, let's just watch this very nice video demonstrating how the viscosity changes as you change the strain rate. So let's see this.
Properties of Newtonian fluids experimentally. Let's start with some warm honey. As you can see here, warm honey flows easily, and it will easily flow around objects, such as this ruler. Placing a force on the honey has no effect on its viscosity. Even if we place a large force on it with a hammer, the honey predictably flows around the hammer.
So from this spoon or from that hammer, they're basically applying a strain rate on the fluid. But you can see that honey, since it is a Newtonian fluid, it does not change its viscosity. Okay, now let's watch some other examples.
If we try this,
now let's take the example of cornstarch.
Different fluid. We'll perform the same test with cornstarch solution. When you pour this solution, it appears to behave much the same way as the honey. When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous. Hammering the fluid with even more force produces even more resistance to flow. Because a cornstarch solution's viscosity changes with an applied force, it is a non-Newtonian fluid.
So what's happening here is, when you're applying the same force but at different times, the viscosity of the cornstarch changes. And as I shown in that graph of stress versus strain rate, for cornstarch this graph goes like this. So as you increase the strain rate, the viscosity value goes on increasing. So when you basically hit the cornstarch with the hammer with a higher force in less time, that is when you are applying more strain rate, the viscosity of the cornstarch increases, right? And similarly, you must have seen some examples on cornstarch like this. So the cornstarch earlier behaves like a
surface.
It behaves like a simple fluid. When you just pour it on some beaker, and can also behave like a solid when you apply more strain rate on that fluid. Okay, so let's quickly go through what we learned from this lecture. So first we derived Hooke's law. From the similar analysis, we derived Newton's law of viscosity. From these two analyses, we saw that for the solids, stress is proportional to strain. However, for fluids, stress is proportional to strain rate. Then in this section, we discussed about Newtonian and non-Newtonian fluids.